very close. We had another little delay thing, so this happens, but we're very close. A couple minutes.
Good evening. My name is Bernie Clark. I'm the president of KCTS, the public network, and it's my privilege to welcome you tonight to a very special evening. KCTS is delighted to be part of the partnership which has brought Dr. Stephen Hawking to our fair city again. We're pleased to be working with Terry Bristol and the Institute for Science, Engineering, and Public Policy in Portland. We partnered with Terry and the Institute 5 years ago when Dr. Stephen Hawking was in this very hall to speak to us. And I know that the experience that we had that night is going to be replicated. You're in for a very special treat tonight. Ladies and gentlemen, please join me in welcoming Bruce Chapman, who will introduce tonight's special guest.
Thank you, Bernie, and thank you, ladies and gentlemen. I also would like to thank Terry Bristol with the Institute for Science, Engineering, and Public Policy in Portland, who really is responsible for bringing Professor Hawking to Seattle. Special thanks also go to Courtyard Marriott for their support on logistics of various kinds. About his work, he said, "If my proposal is correct, I would have succeeded in my ambition to discover how the universe began. But I still don't know why it began." It's a pleasure to have him update us on this and other subjects tonight. Please give a warm Seattle welcome to Professor Stephen W. Hawking.
Can you hear me? I should tell you a little about myself. When I was 21, I was diagnosed as having ALS, or motor neuron disease, and told I had 2 or 3 years to live. Before I was diagnosed with ALS, I was very laid back and bored with life. but the prospect of an early death concentrated my mind wonderfully. I realized that life was good, and that there was a great deal I wanted to do. My condition developed much less rapidly than anyone had expected. Unfortunately, it did not interfere with my great interest, which was understanding how the universe works. I won't describe my scientific career, except to say I think I can feel satisfied with what I have achieved, particularly given that my expectations had been reduced to zero. I can safely say that I'm happier now than I was before my condition appeared. I have also been asked what other career I might have followed. In fact, my ALS ruled out most careers apart from theoretical physics. But before it developed, I had toyed with the idea of being a political leader. I might have been the British Prime Minister. However, I'm glad I left the job to Tony Blair. I think I probably get more job satisfaction than he does. And my work is likely to last longer. After that brief history, I will now give my lecture. Shakespeare's character, Hamlet, said, "I could be bounded in a nutshell, and count myself a king of infinite space." I think what he meant was that although we humans are very limited physically, particularly in my own case, our minds are free to explore the whole universe, and to boldly go where even Star Trek fears to tread. But is the universe actually infinite, or just very large? And is it everlasting, or just long-lived? How could our finite minds comprehend an infinite universe? Isn't it pretentious of us even to make the attempt? At the risk of incurring the fate of Prometheus, who stole fire from the ancient gods for human use, I believe we can, and should, try and understand the universe. As I shall describe in this talk, we have already made remarkable progress in understanding the cosmos, particularly in the last few years. We don't yet have a complete picture, but I think that may not be far off. The most obvious thing about space is that it goes on and on and on. We don't expect the universe to end in a brick wall, though there's no logical reason why it couldn't. But modern instruments like the Hubble Space Telescope allow us to probe deep into space. What we see is billions and billions of galaxies, of various shapes or sizes. There are giant elliptical galaxies, and spiral galaxies like our own. Each galaxy contains billions and billions of stars, many of which will have planets round them. Our own galaxy blocks our view in certain directions, but one can plot the positions of all galaxies in a cone of directions, with us at the point of the cone at the center. As you can see, the galaxies are distributed roughly uniformly throughout space, with some local concentrations and voids. The density of galaxies appears to drop off at very large distances, but that seems to be because they are so far away and faint that we can't make them out. As far as we can tell, the universe goes on in space forever, much the same as it is here. Although the universe seems to be much the same at each position in space, it is definitely changing in time. This was not realized until the early years of this century. Up to then, it was thought the universe was essentially constant in time. It might have existed for an infinite time, but that seemed to lead to absurd conclusions. If stars had been radiating for an infinite time, they would have heated up the universe to their temperature. Even at night, the whole sky would be as bright as the sun, because every line of sight would have ended either on a star or a cloud of dust that had been heated up until it was as hot as the stars. So the observation that you have all made, that the sky at night is dark, is very important. It implies that the universe cannot have existed forever in the state we see today. Something must have happened in the past to make the stars turn on a finite time ago. Then the light from very distant stars wouldn't have had time to reach us yet. This would explain why the sky at night isn't glowing in every direction. If the stars had just been sitting there forever, why did they suddenly light up a few billion years ago? What was the clock that told them it was time to shine? This puzzled those philosophers, like Immanuel Kant, who believed that the universe had existed forever. But for most people, it was consistent with the idea that the universe had been created, much as it is now, only a few thousand years ago. However, discrepancies with this idea began to appear with observations by the 100-inch telescope on Mount Wilson in the 1920s. First of all, Edwin Hubble discovered that many faint patches of light called nebula, were in fact other galaxies, vast collections of stars like our Sun, but at a great distance. In order for them to appear so small and faint, the distances had to be so great that light from them would have taken millions or even billions of years to reach us. This indicated that the beginning of the universe couldn't have been just a few thousand years ago. But the second thing Hubble discovered was even more remarkable. By an analysis of the light from other galaxies, Hubble was able to measure whether they were moving towards us or away. To his great surprise, he found they were nearly all moving away. Moreover, the further they were from us, the faster they were moving away. In other words, the universe is expanding. Galaxies are moving away from each other. The discovery of the expansion of the universe was one of the great intellectual revolutions of the 20th century. It came as a total surprise, and it completely changed the discussion of the origin of the universe. If the galaxies are moving apart, they must have been closer together in the past. From the present rate of expansion, we can estimate that they must have been very close together indeed, about 10 to 15 billion years ago. But maybe the galaxies fell towards each other, just missed colliding, and then moved away from each other, like we see them moving apart today. This idea that there hadn't been a beginning to the universe seemed to be supported by the work of two Russians, Lifshitz and Kolodnikov, and became almost an article of faith in the Soviet Union. The fact that it avoided the awkward question of the creation of the universe was an obvious attraction. In fact, I began my research in cosmology just about the time that Lifshitz and Kolodnikov published their conclusion that the universe didn't have a beginning. I realized that this was a very important question, but I wasn't convinced by the arguments that Lifshitz and Kolodnikov had used. Instead, Roger Penrose and I managed to prove geometrical theorems to show that the universe must have had a beginning if Einstein's general theory of relativity was correct and certain reasonable conditions were satisfied. It is difficult to argue with a mathematical theorem, so in the end Lifshitz and Kolodnikov conceded that the universe should have a beginning. Although the idea of a beginning to the universe might not be very welcome to communist ideas, Ideology was never allowed to stand in the way of science and physics, unlike biology. Physics was needed for the bomb, and it was important that it worked. We are used to the idea that events are caused by earlier events, which in turn are caused by still earlier events. There is a chain of causality, stretching back into the past. But suppose this chain has a beginning, suppose there was a first event. What caused it? This was not a question that many scientists wanted to address. They tried to avoid it, either by claiming, like the Russians, that the universe didn't have a beginning, or they maintained that the origin of the universe did not lie within the realm of science, but belonged to metaphysics or religion. In my opinion, this is not a position any true scientist should take. If the laws of science are suspended at the beginning of the universe, might not they also fail at other times? A law is not a law if it only holds sometimes. I believe that we should try to understand the beginning of the universe on the basis of science. It may be a task beyond our powers, but at least we should make the attempt. The geometrical theorems that Roger Penrose and I proved showed that the universe must have had a beginning, but didn't give much information about the nature of that beginning. They indicated that the universe began in a Big Bang, a point where the whole universe, and everything in it, were scrunched up into a single point of infinite density. At this point, Einstein's general theory of relativity would have broken down. Thus one cannot use it to predict in what manner the universe began. One is left with the origin of the universe, apparently being beyond the scope of science. This was not a conclusion that I, or a number of other people, were happy with. The reason Einstein's general relativity broke down near the Big Bang was that it was what is called a classical theory. That is, it implicitly assumed what seems obvious from common sense, that each particle had a well-defined position and a well-defined speed. In such a so-called classical theory, if one knew the positions and speeds of all the particles in the universe at one time, one could calculate what they would be at any other time, in the past or future. However, in the early 20th century, scientists discovered that they couldn't calculate exactly what would happen on very short distances. It wasn't just that they needed better theories. There seems to be a certain level of randomness or uncertainty in nature that cannot be removed however good our theories. It can be summed up in the uncertainty principle that was formulated in 1925 by the German scientist Werner Heisenberg. One cannot accurately predict both the position and the speed of a particle. The more accurately the position is predicted, the less accurately you will be able to predict the speed, and vice versa. Einstein objected strongly to the idea that the universe is governed by chance. His feelings were summed up in his dictum, "God does not play dice." But all the evidence is that God is quite a gambler. The universe is like a giant casino, with dice being rolled, or wheels being spun, on every occasion. A casino owner risks losing money each time dice are thrown, or the roulette wheel is spun. But over a large number of bets, the odds average out, and the casino owner makes sure they average out in his or her favor. That's why casino owners are so rich. The only chance you have of winning against them is to stake all your money on a few rolls of the dice, or spins of the wheel. It is the same with the universe. When the universe is big, there are a very large number of rolls of the dice, and the results average out to something one can predict. But when the universe is very small, near the Big Bang, there are only a small number of rolls of the dice, and the uncertainty principle is very important. In order to understand the origin of the universe, one therefore has to incorporate the uncertainty principle into Einstein's general theory of relativity. This has been the great challenge in theoretical physics in the last 30 years. We haven't solved it yet, but we have made a lot of progress, and we feel we may be close. Because the universe keeps unrolling the dice to see what happens next, it doesn't have just a single history, as one might have thought. Instead, the universe must have every possible history, each with its own probability. There must be a history of the universe, in which the Seahawks won the Super Bowl, though maybe the probability is low. This idea that the universe has multiple histories may sound like science fiction, but it is now accepted as science fact. It is due to Richard Feynman, who worked at the eminently respectable California Institute of Technology and played the bongo drums in a strip joint up the road. Scientists are now working to combine Einstein's general theory of relativity and Feynman's idea of multiple histories into a complete unified theory that will describe everything that happens in the universe. This unified theory will enable us to calculate how the universe will evolve if we know its state at one time. But the unified theory will not in itself tell us how the universe began, or what its initial state was. For that, we need what are called boundary conditions, things that tell us what happens on the frontiers of the universe, the edges of space and time. But if the frontier of the universe was just at a normal point of space and time, we could go past it and claim the territory beyond as part of the universe. On the other hand, if the boundary of the universe was at a jagged edge, where space and time were scrunched up, and the density was infinite, it would be very difficult to define meaningful boundary conditions. However, Jim Hartle of the University of California, Santa Barbara, and I realized there was a third possibility. Maybe the universe has no boundary in space and time. At first sight, this seems to be in direct contradiction with the geometrical theorems that I mentioned earlier. These show that the universe must have had a beginning, a boundary in time. However, there is another kind of time, called imaginary time, that is at right angles to the ordinary real time that we feel going by. One can follow the history of the universe in imaginary time, and it is very different from the history in real time. In particular, the history of the universe in imaginary time need have no beginning or end. Imaginary time behaves just like another direction in space. Thus, the histories of the universe in imaginary time can be thought of as the curved space of the universe, changing in the imaginary time direction. The histories can therefore be regarded as curved surfaces in the space and imaginary time directions. If they were curved like a saddle, or if they were flat, they would go off to infinity, and one would have the problem of specifying what the boundary conditions were at infinity. But one can avoid having to specify boundary conditions at all if the histories of the universe in imaginary time are closed surfaces, like the surface of the Earth. The surface of the Earth doesn't have any boundaries or edges. I know, because I have been round the world, and I didn't fall off. I even went to Antarctica to check there wasn't an edge there. If the histories of the universe in imaginary time are indeed closed surfaces, as Jim Hartle and I proposed, it would mean the universe is entirely self-contained. It doesn't receive any input from the outside, telling it what it should be like. Instead, everything in the universe would be determined by the laws of science, and by rolls of the dice within the universe. This may sound presumptuous, but it is what I, and many other scientists believe. As I said earlier, even if the boundary condition of the universe is that it has no boundary, it won't have just a single history. Instead, the histories in imaginary time will correspond to every possible closed surface. Each history in imaginary time will determine a history in real time. Thus we have a superabundance of histories for the universe. What picks out the particular history, or set of histories that we live in, from the set of all possible histories of the universe? One point that we can notice is that many of these possible histories of the universe won't go through the sequence of forming galaxies and stars that was essential to our own development. It may be that intelligent beings can evolve without galaxies and stars, but it seems unlikely. Thus the very fact that we exist, as beings that can ask the question, why is the universe the way it is a restriction on the history we live in. It implies it is one of the minority of histories that have galaxies and stars. This is an example of what is called the Anthropic Principle. The Anthropic Principle says that the universe has to be more or less as we see it, because if it were different, there wouldn't be anyone here to observe it. Many scientists dislike the Anthropic Principle because it seems rather hand-waving and not to have much predictive power. But the anthropic principle can be given a precise formulation, and it seems to be essential when dealing with the origin of the universe. M-theory, which is our best candidate for a complete unified theory, allows a very large number of possible histories for the universe. Most of these histories are quite unsuitable for the development of intelligent life. Either they are empty, or too short-lasting, or too highly curved, or wrong in some other way. Yet according to Richard Feynman's multiple histories idea, these uninhabited histories can have quite a high probability. We really don't care how many histories there may be that don't contain intelligent beings. We are interested only in the subset of histories in which intelligent life develops. This intelligent life need not be anything like humans. Little green men would do as well. In fact, they might do rather better. The human race does not have a very good record of intelligent behavior. As an example of the power of the anthropic principle, consider the number of directions in space. It is a matter of common experience that we live in three-dimensional space. That is to say, we can represent the position of a point in space by three numbers. For example, latitude, longitude, and height above sea level. But why is space three-dimensional? Why isn't it 2, or 4, or some other number of dimensions, like in science fiction? In fact, in M-theory, space has 10 dimensions, but it is thought that 7 of the directions are curled up very small, leaving 3 directions that are large and nearly flat. It is like a drinking straw. The surface of a straw is 2-dimensional. However, one direction is curled up into a small circle, so that from a distance, the straw looks like a one-dimensional line. Why don't we live in a history in which 8 of the dimensions are curled up small, leaving only 2 dimensions that we notice? A 2-dimensional animal would have a hard job digesting food. If it had a gut that went right through, like we have, it would divide the animal in 2, and the poor creature would fall apart. So 2 flat directions are not enough for anything as complicated as intelligent life. On the other hand, if there were 4 or more nearly flat directions, the gravitational force between two bodies would increase more rapidly as they approached each other. This would mean that planets would not have stable orbits about their suns. They would either fall into the sun, or escape to the outer darkness and cold. Similarly, the orbits of electrons in atoms would not be stable, so matter as we know it would not exist. Thus, although the multiple histories idea would allow any number of nearly flat directions, only histories with 3 flat directions will contain intelligent beings. Only in such histories will the question be asked, why does space have 3 dimensions? A 3-dimensional universe evolving in imaginary time will be represented by a 4-dimensional curved surface. That is to say, each event in the history of the universe can be labeled by 4 numbers. 3 numbers label the position in space, and the 4th is the imaginary time of the event. The simplest closed 4-dimensional surface is a round sphere, like the surface of the Earth, but with 2 more dimensions. This history in imaginary time determines the history of the universe in the real time that we experience. In this, the universe is the same at every point of space, and it is expanding in time. In these respects, it is like the universe we live in. But the rate of expansion is very rapid, and it keeps on getting faster. Such accelerating expansion is called inflation, because it is like the way prices go up and up at an ever-increasing rate. Inflation in prices is generally held to be a bad thing, but in the case of the universe, inflation is very beneficial. The large amount of expansion smooths out any lumps and bumps there may have been in the early universe. As the universe expands, it borrows energy from the gravitational field to create more matter. The positive matter energy is exactly balanced by the negative gravitational energy, so the total energy is 0. When the universe doubles in size, the matter and gravitational energies both double. So twice 0 is still 0. If only the financial world were so simple. The history of the universe in imaginary time were a perfectly round sphere, the corresponding history in real time would be a universe that continued to expand in an inflationary manner, forever. While the universe is inflating, Matter could not fall together to form galaxies and stars, and life, let alone intelligent life like us, could not develop. Thus, although histories of the universe in imaginary time, that are perfectly round spheres, are allowed by the multiple histories idea, they are not of much interest. However, histories in imaginary time, that are slightly flattened at the North Pole, are much more relevant. The corresponding history in real time will expand in an accelerated, inflationary manner at first. But then the expansion will begin to slow down, and galaxies can form. In order for intelligent life to be able to develop, the flattening at the North Pole must be very slight. This will mean that the universe will expand by an enormous amount. The record of monetary inflation occurred in Germany between the wars, when prices rose billions of times. But the amount of inflation that must have occurred in the universe is at least a billion. Of course, that was before the present government tackled inflation. Because of the uncertainty principle, there won't be just one history of the universe. Instead, the histories in imaginary time will be a whole family of slightly deformed spheres, each of which corresponds to a history in real time that inflates for a long time, but not indefinitely. We can then ask which of these allowable histories is the most probable. It turns out that the most probable histories are not completely smooth, but have tiny ups and downs. When I say tiny, I really mean tiny. The departures from smoothness are of the order of 1 part in 100,000. Nevertheless, although they are so small, we have managed to observe them as small variations in the microwaves that come to us from different directions in space. This is a map of the sky in microwaves, made by the Cosmic Background Explorer satellite. The different colors indicate different temperatures. But the whole range from red to blue is only about a 10,000th of a degree. Yet this is enough variation between different regions of the early universe for some of them to stop expanding and to collapse again under their own gravity, to form galaxies and stars. So look at this map well. It is a blueprint for all the structure in the universe. what will be the future behavior of the most probable histories of the universe. There seem to be various possibilities which are compatible with the appearance of intelligent beings. They depend on the amount of matter in the universe. If there is more than a certain critical amount, the gravitational attraction between the galaxies will slow them down and will eventually stop them flying apart. They will then start falling towards each other and will all come together in a big crunch. That will be the end of the history of the universe in real time. When I was in Japan, I was asked not to mention the big crunch because of the effect it might have on the market. But the markets have been very volatile, so maybe the story got out somehow. If the density of the universe is below the critical value, gravity is too weak to stop the galaxies flying apart forever. All the stars will burn out, and the universe will get emptier and emptier, and colder. So again, things will come to an end, but in a less dramatic way. Still, we have a few billion years in hand. As well as matter, the universe may contain what is called vacuum energy, energy that is present even in apparently empty space. By Einstein's famous equation, E equals mc squared, this vacuum energy has mass. This means that it has a gravitational effect on the expansion of the universe. But remarkably enough, the effect of vacuum energy is the opposite of that of matter. Matter causes the expansion to slow down, and can eventually stop and reverse it. On the other hand, vacuum energy causes the expansion to accelerate, like in inflation. We can therefore try to determine the amounts of matter and vacuum energy in the universe from various observations. One can show the results in a diagram in which the matter density is the horizontal direction and vacuum energy is the vertical direction. The dotted line shows the boundary of the region in which intelligent life could develop. If the matter density and vacuum energy lie outside this region, galaxies wouldn't have formed, and we wouldn't be here to ask what the matter and vacuum energy were. Observations of supernovas indicate that the values probably lie in the elliptical region colored red. Observations of how much matter is clustered suggest the values lie in the blue region. And observations of the microwaves from space indicate that the values lie in the purple region. Fortunately, all three regions have a common intersection. If the matter density and vacuum energy lie in this intersection, it means that the expansion of the universe has begun to speed up again, after a long period of slowing down. Despite what politicians may tell you, we have not seen the end of inflation. It seems that inflation may be a law of nature. In this lecture, I have tried to explain how the behavior of the vast universe can be understood in terms of its history in imaginary time. This is a tiny, slightly flattened sphere. So it is quite like the nutshell with which I began the lecture. Yet this nut encodes everything that happens in real time. So Hamlet was quite right. We could be bounded in a nutshell and count ourselves kings of infinite space. What more can I say after that?